Good evening, everyone. I welcome you to the penultimate lecture of STEM's 2022 lecture series. Today, we are quite happy to have Professor Shubhangi Saraf with us. So, let me give you a brief introduction about her. She is a associate professor at the University of Toronto in the Computer Science and Mathematics department. She completed her PhD in the prestigious MIT under the supervision of Professor Madhusudan. Her research interests are in complexity theory, error correcting codes, discrete geometry, and in general, the theoretical computer science area. Today, she will be talking about error correcting codes and some fun applications of polynomials in theoretical computer science. And so, before we begin, just a couple of quick points. If you have any questions, feel free to drop them in the chat, or you can unmute yourself and ask directly to the professor. And also, it would be great if people can turn on their videos so we can reach closer to a live interaction. And I think now we can start. Thank you, Professor Shubhangi. And
Thank you, Amik. Thank you, Amik and Anuridhan, for inviting me to this seminar series. I'm really happy to be giving a talk here and to see all of you. And I will tell you all about error correcting codes. Please do take the opportunity to ask questions. I really encourage that. Okay, so it will help me pace the talk and make sure that I am not going too fast. Okay, good. So, 1 second. Is my sorry. Good. Let me move this to this side. Okay, great. So the setting which I want to talk about is where you have a huge amount of information. There's information which gets stored on DVDs or data centers. There's information which gets communicated via cell phones or satellite. And often in situations, there's noise is inevitable. So when data is transmitted, it's often over a noisy channel, or the medium it's stored on is unreliable. So for instance, a DVD over time might develop a scratch, or if you have communication over cell phones and satellites, there may be external reasons for which errors get introduced. And in situations, oftentimes, reliability of the data is absolutely critical. For instance, if you want to send a message saying we are not ready and there's noise, the receiver might, even a teeny amount of noise could completely alter the meaning of the message being conveyed. And sometimes this is just not an option. And so, for instance, for reliable information storage, if you're going to store information in a DVD today and you want to retrieve it many years from now, Shannon, several decades ago, studied this model and said you can model the passage of time as a noisy channel. Okay, so as time progresses, your data gets errors in it. And Shannon came up with a quite brilliant solution, which is when you have your data, don't store it as is on the DVD. Use something called an error correcting code. Take your data, encode it by a code, then store it, so that once you store the data over many years, maybe some corruptions will occur in the data. But then later on, you can take this corrupted data, pass it through a decoder, and hope that at the end you've recovered the true uncorrupted original data. Okay, so and how we do this is what I'll talk about a little bit. So the consequence of this scheme by Shannon is that today we do know how to have very good error correcting codes which can protect against a large number of errors. So I'll tell you a little bit about error correcting codes. We'll see some basic bounds. I'll talk about Reed-Solomon codes, which are a very nice, elegant, and a strong family of error correcting codes. We'll see some applications, and I'll also mention locally decodable codes. Okay, so this is the scheme we want to enable. There's your data, you encode it, then some corruptions occur, and then you can somehow decode it and get your original data. So let me give you an example of an error correcting code, a very simple code when you have the promise that at most one bit of your data gets corrupted or flipped. Okay, so let me elaborate. So you start off with a message, that's the data you have. It is of length k is some parameter, and imagine that your data now is a string of zeros and ones. You have this data of zeros and ones, and you want to is a question?
No.
Okay, so you have your data, which is a string of zeros and ones, and we want to do something to this data, which will or encode it so that even if one of the zeros became a 1 or a 1 became a 0, we still don't lose the information. The exact original data is received. Okay, so what can you do to this data? And there's a simple, nice scheme which works, which is you take your data, your string of zeros and ones, and you take each bit in this data, each 0 or 1, and you replicate it 3 times. Okay, so for instance, if your data that you wanted to store was 11011, the encoding scheme for this data is you take the first one and you write it 3 times. Take the second one, you write it 3 times. You take the 0, you write it 3 times, and so on and so forth. You triplicate your data. This is the encoding. So when you want to store your data on the DVD, instead store this encoded data. And the nice property that this encoding has is that suppose later one of the bits got corrupted. Okay, so some 1 became a 0 or some 0 became a 1. That's not really a problem, because later when you want to recover the original data, there's a very simple scheme for recovering the original data. You can look at each block of 3 bits and take the majority vote from that block. So the 111 gets decoded to a 1. The 101 must have started off from a 1 if the number of corruptions is at most 1. So this is a scheme which allows you to decode from 1 bit error, and this is like the example of like the simplest error correcting code. Okay, so this means using this scheme, if you had a message which was of length 120 or 120 bits, you could encode it to a 360 bit long code word.
And I'm very sorry for interrupting. I have a question.
Yes.
How do we know that only like 1 bit will get corrupted? What if 2 bits of the same block get corrupted out of 3?
Great question. So I was describing a code where we made an assumption that there's only 1 bit, and we're saying, okay, let's see what is the best you can do when you are imagining that there's only 1 bit that will get corrupted.
Okay, I got it.
But this is just the simplest example. Then the next question to ask is absolutely, what if there are going to be 2 corruptions or 10 corruptions? We do know that if the number of corruptions is too many, maybe there's no hope, right? If the whole thing gets erased and replaced with something else, there's just no chance. So for every code, you need to specify, okay, I believe the number of corruptions will be at most something, and let's design a code which can handle so many corruptions. So that's exactly the kind of questions we want to be looking at. But now this is a simple assumption, just to simplify matters, just we assume that it's just 1 bit that gets corrupted. And what is the best that you can do? So thanks for clarifying that. Okay, so we are assuming there's only 1 bit of corruption. What's the best you can do? And this gave you a scheme where you can now, suppose your message was 120 bits long, you can map it to a code word which is 360 bits long. It's an extremely efficient encoding and decoding scheme, and everything is nice about it. But there's one bad news is, of course this scheme only corrects from 1 error, but let's assume we are in the setting where there's only 1 error. But another bad news is that the rate of the code is not so great. So I define the rate of the code to be the ratio of the message length to the code word length. And the rate is not so good because the rate here is 1/3. You had to really triplicate your data, right? A string of length 120 had to get blown up to a string of length 360 in order to do this. it's possibly wasteful if you can do it better. So a good question is, can you do this better than just repeating every bit 3 times? And if you can do better, how much better can you do? And so this question was studied by Hamming in 1950, so as far back as then. And he said, yes, you can do better. And then he gave ways of doing better. And I will tell you one way of doing better. So you can, instead of taking each bit and replicating it 3 times, you can take your data and you can break it up into chunks of 4 blocks. No, I didn't mean to say that. You break it up into chunks where each chunk or chunks or blocks where each block has 4 bits in it. Because your long data, you cut it up into little pieces of 4 bits each. And each little block of 4 bits, we will separately encode. Okay, so this is one thing you can do. You take your block of 4 bits. Suppose your block is 1101. The way you take your block and you encode it is you take 1101 and you multiply it by a certain matrix. Okay, so I've given you a 4 by 7 matrix. It has zeros and ones. And I say take your block, multiply it by this matrix, and that is the encoding of the block. And when I say multiply by the matrix, what we did was do everything mod 2. So you can, all the additions and multiplications, everything is going mod 2. So you can multiply it over the integers if you like, but then you take your answer and then each symbol, each integer you go mod 2. And then eventually that's how you get a string of zeros and ones. Okay, so where did this so a little bit of a mystery. Why did I choose this matrix? What's so good about this matrix? It took a string of, this matrix gave me a way of taking a string of length 4 and mapping it to a string of length 7. The encoding is going to say, do this for the whole data. You chop it up into these blocks of length 4. Each one you multiply by the same matrix. You get a string of length 7. And then you concatenate all these strings of length 7, one after another. And the reason this matrix is nice, I won't say too much, and this is something to go later think about why it works, is that if 2 messages are different, so if you have 2 strings of length 4 which are different, and by different I mean they might differ in just one location or many locations, it doesn't matter, but you take any 2 strings of length 4, and if they're different, then the encoding of these strings will be very different. So you start with M1 and M2 which differ in 1 bit, then you take M1 and you multiply it by this matrix G, you take M2 and you multiply it by this matrix G, then the output or the encoding will be quite different. It will differ in at least 3 coordinates. This matrix has that property. One needs to prove that. It's not so hard, but I won't do it now, just in interest of time. But once you can ensure that the encoding of any 2 messages differs in at least 3 coordinates, it turns out that that is enough to guarantee that you can decode this code from 1 error. Okay, I'll talk more about why differing in 3 coordinates is enough to recover from 1 error. But notice that, assuming you all believe me that this scheme works, you can now take a message which was length 120, and by this scheme, instead of mapping it to a code word of length 360, you can map it to a code word of length 210. Because this 120 bit long message, you chopped it up into 40 different, you have blocks of length 4, 30 different blocks of length 4. Each block of length 4 got mapped to a block of length 7. And then you put all these blocks of length 7 one after the other. That gives you a total code word length of 210. And it still corrects from 1 bit of error. You can use it to correct from 1 bit of error. And so the rate of this code is much better, because 120 bits now only mapped to 210 bits. And can we do better? And it turns out that we can do better. Hamming developed this whole theory of Hamming codes. And in fact, there's a way of correcting from 1 error. So you notice that we don't know where the error is, right? We want a scheme to correct from 1 error when also you have absolutely no knowledge of where that error is. And Hamming showed that there is a way of mapping 120 bits to just 127 bits. So far more efficient than what we have talked about. And it can correct from one bit of error, and Hamming was able to show that this is the best possible. There is no scheme mapping 120 bits to 126 bits, which can correct from one error. These are called Hamming codes. For those of you interested, just go and just do a Google search for Hamming codes. These are well understood, well studied. This is something, the proof of this is something you might be able to understand just by looking it up in lecture notes or any resource you find. It's a really beautiful family of codes. Okay, so let me just explain the notation and terminology around error correcting codes a little bit more before we talk more about it. So right now when I talked about error correcting codes, I talked about bits. Our message was in zeros and ones and the encoding was in zeros and ones. In general, this need not be the case. So you can describe codes over any alphabet. So it could be the English alphabet. Your message could be a string with English letters and the encoding could be a string of English letters, and that's okay. Often, so the alphabet we will talk about when in the talk, I'll talk about something called finite fields. And for those of you who haven't heard about it, don't worry, I'll say a few words about it. But you can have a code over any alphabet. The code should have an encoding scheme, a way of mapping your message or your data into a code word. It normally takes, the code word is, in order to be able to correct from errors, normally the code word, or not normally, always the code word will need to be longer than the message. So you're introducing some amount of redundancy, which eventually allows you to correct from errors. So you have an encoding scheme, taking strings of length k and mapping it to strings of length n. So we'll use n to denote the code word length, k to denote the message length. You think of your encoding mapping data to a code word, and the underlying code is just the image of this function. So you look at, so your encoding was a function mapping strings to code words. All possible code words that you can get under such an encoding scheme, together they form the code. So note that each code word is a string of length n. So you think of your universe as sigma to the power n. It's a set of all strings of length n over the underlying alphabet. And your code words are some subset of sigma to the n. How large is this subset? It's the size of sigma to the power k, right? Because every message gives you a code word. How many possible messages are there? Since your message must be a string of length k, the total number of messages is the total number of possible strings of length k. So you have about sigma to the power k code words sitting inside this space of yours which has size sigma to the n. Good. So if I identify a particular code word C, it is some string which is of length n. And then with the passage of time, suppose I had written down the code word C on my DVD, with the passage of time some corruptions occur. And then what might be written later on this DVD is not C anymore, but the string R. This is the corrupted code word or the received word. And what you want out of a code is to have any two code words be really far apart. So if all the code, like all these yellow dots which I've placed, which are the code words, if these are all spaced far apart, then one hopes that now if you start from any true code word, which was what was written on the DVD, and if a few corruptions occur and what you end up with is this received string R, the hope is that now when you see R, you can determine which code word it came from. Since all code words are so far apart, the true code word will be the only nearby code word to R. And that's why we want, and if all code words are far apart, we can disambiguate, pick the closest one and know that that's the true code word. And that's how you do decoding of error correcting codes, to find this nearest code word. And in order to handle enough errors, one error or two errors or more errors, you want these code words to be sufficiently far apart. Okay, so again, what is the decoding scheme? You look at your received word, you look in a neighborhood of the received word and see which are the code words which are near you, and then pick the nearest code word. That's how decoding works. And when I talk about distance, like I want to look at what are the strings or the true code words near R, what notion of distance are we using? It's not Euclidean distance, it's Hamming distance. Because, so let me define what the Hamming distance. So given two strings x and y of the same length, delta of xy, or the Hamming distance between those two strings, I define to be the number of locations in which these two strings are different. It's the number of coordinates I for which the ith symbol of x and the ith symbol of y are different. So for instance, if I have these two strings 10110 and 10011, then what's the Hamming distance? The first and second coordinates are the same, but the third coordinate of both strings is different, and the fifth coordinate of both strings is different. And so the Hamming distance of these two strings is 2. Okay, so that's a measure of how similar or different two strings are. The distance of a code we define to be the minimum over all pairs of code words of the distance between x and y. It's the min over all x, y in the code. So look at all pairs of code words, look at their distance between pairs of them and take the smallest distance you see. That's the distance of the code. And so if I say the distance of the code is some number d, that means that every two code words differ in at least d coordinates. And let's prove this really simple lemma, which is that if you have a code of distance 2t plus 1 or at least 2t plus 1, okay, so any two code words are at least 2t plus 1 apart, then this code will be able to correct as many as t errors. So in order to be able to correct from t errors, if we can design a code of distance 2t plus 1, that's good enough. Let's see why. So let's start with a code which has distance 2t plus 1. What does it mean? That means in out of my space sigma to the n, which is all possible strings of length n, I have found a subset which are the code words, and the distance between any two, and the Hamming distance between any two code words is at least 2t plus 1. Now I had written my data in the form of a code word on, say, the DVD, and then over time some corruptions occurred, and I want to show that we can correct for up to t corruptions or t errors. So I started with the code, I made at most t errors over time, and then the new string that is written down on the DVD many years later is the string r. Okay, and we know that r is at most distance t away from c. So then how would you decode the original data? Again, you would look at that string r, you will look at a ball of radius r or a radius t around r. And by ball of radius t, it means I look at all possible strings of distance at most t from r. And since you know that the r and c are close in this distance, the at most t corruptions to get from c to r, you know that the true code word you're looking for sits inside this ball of radius t. And I want to say, notice that there will be no other code word. There will be a unique code word in this ball of radius t. And that is because suppose there were two code words in this ball, but the ball has only radius t. So that means to get from r to any code word in this ball, you can get to it by just t corruptions. Then you can see that if there were two code words in this ball, then those two code words would have distance at most 2t between them. This is some triangle inequality, because the distance of each code word in the ball from r is at most t. By the triangle inequality, if you had two code words, the distance between them would have been at most 2t, but that's not possible because you started with a code of distance 2t plus 1 at least. Okay, so in a ball of radius t around r, there'll be a unique code word, and that's how you do the decoding. So you find that true code word which is sitting in the true unique code word sitting in a ball of radius t around r. So that's how you can recover, you can realize that what were the errors made, you can recover what the true code word was, and once you recover the true code word, you can recover the true message by inverting this encoding map. And that's how you can codes of large distance can correct many errors. And there's the algorithmic question, which I didn't talk too much about, which is, I said, okay, how do you decode how do you correct from the errors? You look at the string R and you search in this ball of radius t around R for which code words are there, and there'll be only one code word. But searching in this ball of radius t, or looking at all strings of distance at most t from R, could be extremely a very slow process, and depending on what t is, it could be an exponential time algorithm. And so there's the very natural question and obvious question that comes up is that how do you do this efficiently? Ideally, you want a code where this decoding process can also be done very quickly to make it useful in practice. Okay, so I talked about Hamming distance and distance of a code. There are 4 main parameters associated with a code. One is the length of the code, the length of the message, the distance of the code, and the alphabet. And
so, ma'am, I have one question here.
Yes.
So, when you define the distance to be the minimum over all xy, can we do something different? So, suppose like my code words have like almost every code word has some like maybe 3D or 4D distance, but only one pair of them has a small distance. But the chance of occurring that code word is really small. So, I can ignore that one and take 4D as my distance.
Yes, so good. So if you know that your message, this was also doing some worst case. Like, I don't know what my message is. I want to be able to decode no matter what the message is.
Right.
Then what do you do? But yes, there are models which study differences in. I mean, if you have if you don't want, you can change the model, and there are tons of variations on the questions you can study. Like what you said, I mean, you can study models where, I mean, for instance, can you maybe the code you are giving, maybe you can modify it. Like I remove that one string and I do something special with it and encode it and don't affect the rate much. People study questions where the error is not adversarial, but the error is randomly introduced. So that's something a little bit more information, then maybe you can do better. Or yeah, so what you asked is an absolutely valid question, and that in real world scenarios there are lots of added assumptions that you might know, or added things you might know about what the message space looks like or how the corruptions occur, and then you can take that information into account and design codes tailored to that situation. So right now, yeah, I'm just studying this just because of the cleanliness of the model. Let's assume that you need all the distance to be large, because your data could be any of these, could result in any of these code words with no assumption. But absolutely, I mean, there's lots of variations you can study, and in different and these codes are actually extremely practically relevant. So what I'm talking about error correcting codes, I mean, this error correcting codes in all these, in DVDs, in communication networks, the error correcting codes out in practice everywhere. And they're very nice mathematical questions that arise in the study of codes, which have very significant practical relevance. And different settings need different kinds of codes, not just these codes which I am talking about, which have worst case error and you don't know anything about the message and things like that. Okay, so there are 4 parameters with the code that are interesting. One is the code word length, the message length, the distance, and the alphabet. So what do we want? How do these parameters relate? So ideally, we want k to be as big as possible and n to be as small as possible, so that these codes have good rate, right? As low redundancy, you're wasting that much less space in communication or storage. So we want n, for every fixed k, we want n to be as small as possible, and we want the distance d to be as large as possible, so that the code can handle many errors. The larger that you can make d, the more errors the code can tolerate, so the more robust the code is to corruptions or errors. What do you want the alphabet size to be? So it depends. In different scenarios, it could be different. We won't talk too much about it. Often, when you have codes over large alphabets, you can do some operation on it to make it a code over a small alphabet, maybe with some loss in parameters. But we won't talk about the alphabet too much. In different situations, different alphabets make sense. And so the question is, what are the best trade-offs you can achieve? Can you get a code of really high rate but also large distance? Or what's the best for every rate? What's the largest distance you can achieve? Okay, these are very natural questions that arise. So the combinatorial questions that arise is design the best possible error correcting codes. And for me, best possible is, if I want the rate to be, say, half, so k goes to 2k bits, what's the best possible distance you can achieve? So what's the best, combinatorially, try to get the best possible trade-offs between the rate of the code and the distance of the code. And then there's the algorithmic question. For every combinatorial code which is good, you have to ask for it to be relevant in practice. You need algorithms which support efficient encoding and decoding of these codes. So there may be codes which are very good, but working with these codes, just in computing the encoding function or computing the decoding function, that might be really inefficient, and that makes the code not useful at all. So there, in the study of error correcting codes, there's combinatorics and algorithms both play a very important role. And okay, so why study codes? One is real data storage, real data transmission. These are indispensable in practice. And it turns out that these error correcting codes, not just for practice, they also have a lot of applications by themselves to lots of areas of computer science. So my research is in theoretical computer science, and codes come up all the time, not just for the practical application, but just because of connections to questions in cryptography and complexity theory, communication complexity, lower bounds, learning theory. So there's a whole bunch of buzzwords. I won't talk much about it, but codes are useful everywhere. And let me tell you some very basic bounds about, what time is it? 8:32. Okay. Let me tell you some basic bounds that we know about error correcting codes. Okay, so the first understanding of what these rate distance trade-offs could look like. So if you have a code of distance 2t plus 1, so we know it can correct up to t errors. The ball about the point x of radius r is all those strings of distance at most r from x. Okay, so here's one understanding of codes, the Hamming bound, which is if you have a code of distance 2t plus 1, then if you draw balls of radius t around each code word, these balls of radius t must be disjoint. Because if these balls were not disjoint and they intersected, then the corresponding centers of those balls would be of distance at most 2t from each other, and that's not possible in a code of distance 2t plus 1. So balls of radius t are disjoint, which means that look at what's the size or the volume of a ball. The volume of a ball is the number of strings that fit inside a ball. Then the number of code words times the number of strings in a ball, that's at most q to the n. Q to the n is the size of the full space. So this tells you that the number of code words cannot be too large, because the number of code words times the size of each ball is at most q to the n. That's one basic bound. That tells you can't have too large a number of code words, and your rate can't be too large for any distance. Here's another basic bound. Suppose you took the best possible code there was. Okay, so you packed as many points as you could inside your space where the distance is at least 2t plus 1. So it's a maximal code, with any two code words being of distance 2t plus 1. Then if you look at a ball of radius 2t around every code word, not 2t, look at balls of radius 2t, then these balls need to cover all of sigma to the n. Why? Because if I take all these balls of radius 2t about the code words, if they don't cover all of sigma to the n, then any point which is not covered, I can add it into the code. And I can grow my code by one more. And I will maintain that the distance still remains 2t. So the best possible, if you take the best possible code, it must be that the number of code words times the size of each of these balls is at least q to the n, because these balls of radius 2t around all the code words cover all of q to the n. This tells you that these good codes or the best possible codes can be pretty large. The size of the code is at least q to the n divided by the volume of the ball. And so by both these bounds that I gave you, it gives some understanding of what are the best rate distance trade-offs achievable by codes. And the basic question that we want to understand is how many code words can you fit inside sigma to the n, or how many strings can you fit inside sigma to the n so that any two have distance d. And it turns out that we don't really know the answer in general. For d, whether d is very small or for very specific settings, sometimes we know the answer, but most of the times we're far from knowing the true answer about what's this best packing problem. How many strings can you fit inside sigma to the n where any two have distance d? So that's a big open question in error correcting codes. Just what's the best rate distance trade-off you can achieve? And so again, many of the very basic fundamental questions remain open about error correcting codes. But we do know that though we don't know the best rate distance trade-offs, we still do know a lot. We know lots of ways of constructing good codes in various situations. And I will tell you about one family of codes, the polynomial based family of codes. I'll talk about it. These are called Reed-Solomon codes. So in this next few minutes, I'll describe what Reed-Solomon codes are. They're a really elegant family.
How would we know if we have got the best code?
Good question. So if you know, so in each, so the best code I showed you must have the number of code words being large enough. This was this GV bound. You might construct a code by some other means. I mean, I'll give you one way of constructing polynomial codes, these Reed-Solomon codes. You might construct codes from some other means and then mathematically prove that, look, the rate is large and the distance is large. And if you can see that so the best, how will you know that how will you every code that you construct, you can compute by yourself, not compute by yourself. You might be able to prove using properties of whatever construction that you've used that the rate is really large and the distance is really large. And if you know the best, that for every rate, the distance can be at most so much, and you manage to prove that the distance is really good, maybe you got the best possible code. So today we know how to construct codes by a bunch of means, and we can compute what is the rate and what is the distance.
Okay.
It's just, can you construct a code with for that same rate, can you construct a code with better distance? So
Okay, got it.
Okay, I don't think my answer was too clear, but if you got it, that's good.
I mean, yeah, I got it.
Each code is like so I'll give you an example of a code now, and we'll compute the rate and the distance of that code. Okay, so these are polynomial based codes, Reed-Solomon codes, which are have been studied for decades, and these are ubiquitous. I mean, they show up everywhere in practice and in theory also. So we'll work with polynomials. I'll use polynomials to describe a family of codes for you. These will be codes not over the 0-1 alphabet. It will be easy to describe it over a large alphabet. But when I work with polynomials, I need to tell you how these polynomials look. What are the coefficients of the polynomials? So usually when we have worked with polynomials, you work with the coefficients being real numbers or integers or complex numbers. We'll be working with polynomials where the coefficients come from a finite field. Again, some of you might know what finite fields are, some of you may not. But just think of a finite field to be a finite set of numbers. Think of, and the best way to think about it is integers modulo a prime. So think of some prime, say I don't know, 37, and you look at only integers mod 37. That's a set. That's a set of size 37. You can add two numbers and multiply two numbers and stay within this set. Similarly, you can define polynomials over this set where the coefficients come from this field or these integers mod a prime, and then you evaluate it at any point in this set, and the evaluation stays also within this finite set. So you can define polynomials where the integers are, where the coefficients are integers mod a particular fixed prime. And these are the kinds of polynomials we will look at. Any questions about that? Stop me and ask me. Okay, so we fix a finite field, and our alphabet is going to be the field elements. What we'll do is we pick our field, we'll pick n distinct elements from our field. So if you have integers, so if n is 30 and our field was size 37, then we'll pick 30 different elements out of our field of size 37. Now, given once we've picked our field, once we've picked n different elements from our field, let's fix these. And now I'll give you a way of constructing a code. I have a message m, which I want to encode. My alphabet is this sigma is this field, right? So my message is a string of length k, and each element of my message is a field element. Good. So how do we encode it? What we'll do is we'll take this message, which is the string of length k, and we'll interpret that message as a polynomial. So we'll use that message and construct it from it a degree k minus 1 polynomial, where we'll put the symbols in your message as you'll make those the coefficients of the polynomial. So given a message, interpret it as a polynomial, and then the encoding is, once you interpret it as a polynomial, take that polynomial and evaluate that polynomial at a bunch of points. Which bunch of points? The n points that you chose before. A1 to an were n points we had chosen and fixed in the beginning. Take those n points and just evaluate the polynomial at those n points. You got a string of length n. That's the code. Okay, extremely nice and easy to describe. So let me give just more concretely. Suppose your field was f11, which is integers mod 11, and your message length is 5, your code word length is 9. Okay, suppose you wanted to get a code mapping k bits to 5 bits to 9 bits, and you're working over f11. Then I'll first choose some 9 elements, a1, a2 up to a9, sitting inside my field. Suppose I want to encode the message 37445. How do I do it? Out of 37445, I first view 37445 as a polynomial. 3 plus 7x plus 4x squared plus 4x cubed plus 5x to the 4. And I take this polynomial and then I evaluate it at a1, a2, a3, a4, a9. I just put all these evaluations one after the other. That's the encoding of the polynomial. That's the encoding of the message. And that's the full description of the code. Very natural, it has very nice properties, and the fact that it is so easy to describe and makes it have very nice encoding, decoding algorithms. It's a very natural family of codes. So this is the code I gave you, which you could have designed this code for any k and any n. Right? So if I got a code mapping k symbols to n symbols, so the rate is k over n. I could have chosen whatever k, whatever n I wanted. What is the distance of this code? And what's remarkable is that these codes have really good distance, and we'll argue that these codes have good distance, and what we'll use is this very simple fundamental fact about algebra. A non-zero univariate polynomial of degree d has at most d zeros, at most d roots. A degree d polynomial can have at most d roots. From this very simple fact, we will deduce that the distance of these codes is n minus k plus 1. Okay, these are codes mapping k bits to n bits. The distance is n minus k plus 1. I'll prove it just now. Which means that any two code words can agree in at most k minus 1 locations. If two strings of length n, If they agree in at most k minus 1 locations, that means they have to disagree in the remaining locations, and that's why the distance is large. Okay. I will not prove it today, but this distance of Reed-Solomon codes is actually the best possible distance you can achieve. For a given rate, these are the codes which have the best possible distance. I had said that we don't know the best possible rate distance trade-off, but in our setting where the alphabet size is large, when the alphabet size ended up being larger than n, we do know the best possible rate distance trade-off, and Reed-Solomon codes achieve it. These are over large alphabets, the best possible codes you can get. So let me tell you why these Reed-Solomon codes have such large distance. So I said that the two code words can agree in at most k minus 1 locations. Why is that? So I take two different code words. They are the encodings of two messages, M1 and M2. Right? So if C1 is the first code word, that means you took M1, you constructed from it this polynomial PM1, and you evaluated it at a bunch of points. For the code word C2, there was a different message M2. It corresponded to code word, and you took that polynomial and you evaluated it at a bunch of points. And I want to say, suppose C1 and C2 agree on more than k minus 1 locations. Suppose they agree on k locations. What does that mean? It means that these two polynomials PM1 and PM2, they take the same value at k different locations, at k different inputs. Two polynomials take the same value on different inputs means that PM1 minus PM2, take the difference polynomial, that takes the value 0 on k different inputs. But PM1 minus PM2 cannot take the value 0 at k inputs, because it's PM1 minus PM2 is a non-zero polynomial of degree at most k minus 1. And a non-zero polynomial of degree k minus 1 can have at most k minus 1 roots. And that's it. So that proves that these two code words can't agree too often, and so this code has really good distance. These codes, as I mentioned, they have these optimal rate distance trade-offs, widely used in practice. We didn't talk about the decoding algorithms, but they end up having a very efficient, simple encoding, decoding algorithms, and they have tons of applications all over computer science. What I will do now, are there any questions about Reed-Solomon codes?
So I have just one, maybe, I don't know whether it is a valid question or not, but this property was due to the polynomials having like the degree. So like, does polynomial only satisfy these properties, or something different can also some different algebraic object can also satisfy? May not be the best possible code, but like, yeah, let's close to the best possible.
Okay, so let me just out of interest in time, I don't have a good answer.
Sorry, I think I muted you by mistake. Yes.
So we have other ways of constructing codes. So once it's we do have lots of ways of achieving codes of good distance. This is not the only one. I do believe that this is basically the only one we know for optimal distance. But for other versions of distance, we have other ways of constructing codes with pretty good distance. But yeah, these algebraic ways somehow end up doing, in many situations, much better than non-algebraic ways. There are combinatorial ways of creating objects which also give you pretty good distance. But I don't know how to achieve optimal distance without using polynomials. I don't didn't answer, but let me keep going for now. So let me give you an application just to see the power. So Reed-Solomon codes are used in practice everywhere. But let's see an application of these codes in a completely different setting, in not an information error. We're not trying to correct from errors, but these codes will still be useful. So the application is to some question in communication complexity. So let me tell you what it is. So you have two people, Alice and Bob, and maybe they're on different parts of the world. Alice holds a string x, which is x1, an n symbol long or n bit long string, and Bob has his own n bit long string, and they are far away. Communication between them is extremely expensive, so they want to say as little as possible, or they want to exchange as few messages or as few bits as possible, and they want to decide if their strings are the same. The goal is to decide, is x equal to y or is x not equal to y? I don't care how different they are, if they differ in 5 locations or 2 locations or 1. I just want to decide, are their strings identical or not? Okay, so how will you do it? And one way to do it, which is obvious or the most natural way, maybe Alice will send her whole input over to Bob. Bob will check, that's n bits of communication. Bob will see if, once Bob gets it, Bob can check if x is equal to y or not and tell Alice the answer, equal or not equal. And this needs n plus 1 bits of communication. Alice had to send n bits, Bob had to reply saying yes or no or 0 or 1. So this needs n plus 1 bits of communication, and turns out this is optimal. You can't do better than this if I want to decide if these strings are equal or not. But let me give you a randomized algorithm. Using randomness, I'll present to you an algorithm which does really well with much less communication. So here's a randomized algorithm for deciding if the two strings are equal or not. Alice and Bob, what they do is separately, they're in both separate parts of the world, each of them encodes their strings using a Reed-Solomon code. Okay, there's a fixed Reed-Solomon code they decided on before or whatever. They know there's a Reed-Solomon code. Alice encodes her string using a Reed-Solomon code. Bob encodes his string using a Reed-Solomon code, and make the distance of the Reed-Solomon code large. So if their strings have length n, so make the distance of the Reed-Solomon code 9 times n. By whatever we talked about, you can achieve this by making the code word length something like 10n. You can take 9n bits, map it to a string of length 10n, and make sure that the code word, the distance is 9n. Okay, so Alice and Bob do this encoding. Let C of x be Alice's code word and C of y be Bob's code word. Then what Alice does is that she picks now she has a code word of length 10 times n. She chooses a random location, a random coordinate out of her code word. So a random I between 1 and 10n she picks, and she tells Bob what that I is and what the ith symbol of the code word is. So she sends I and the ith symbol of her code. What does Bob do? He checks whether the ith symbol of Alice's code word, whether it matches the ith symbol of his code word. If it matches, he announces, good, the strings are equal. Otherwise, he says they're not equal. Okay, so let's understand what just happened, right? If the two strings are truly equal, then Alice's code word will equal Bob's code word. And so when Alice sends the ith symbol and Bob compares it with his ith symbol, they will be the same. And so these Alice and Bob will then conjecture or guess that their strings are equal, and they'll be correct. But what happens if these two strings are not the same? If x is not equal to y? If x is not equal to y, something really nice happened by using Reed-Solomon codes. It could be that x is not equal to y because they just differ in one location. These are humongously long strings, but they just differed in one location. To be able to detect that they differ in one location is quite hard without a lot of communication. But if you use error correcting codes, then even if x and y differ in one location, the encoding of x and the encoding of y will differ in 9 times n locations. In 90% of the locations, you can make them different. So now Alice and Bob have to check if their strings are equal or not. But if they're equal, they're equal. If they're not equal a lot. In 90% of the locations, they'll be not equal. And so when Alice sends a randomly chosen coordinate and sends it to Bob, with 90% probability, Bob will be able to detect that these strings are different, because Cx of I and Cy at I will be different. And so the algorithm will succeed. I mean, these two people will be able to detect if the strings are correct or not. But there'll be an error of at most 10%. Right? Because they were in 90% of the coordinates, they were different. So if I choose a random coordinate, I will detect the difference with high probability, with probability at least 90%. Okay, so what just happened? So let's see. One is to note is there's one bad thing about this algorithm, that it didn't always get the right answer. And it turns out if you want to make an error 0, you will not be able to do this without a lot of communication. But I give you a scheme for detecting if there was error, which succeeds with probability 90%. It won't take you much effort to think about how to make this succeed with 99% or 99.99%. You can now work out the parameters and see how to make this scheme robust to a lot, to get the correct answer with much higher probability. And you will be able to do this without much loss in parameters. 90% was just an example. You can really make the error very tiny. And let's see how much communication we had, right? So how many bits did Alice have to communicate to Bob in this scheme? She had to tell what I is, the randomly chosen coordinate between 1 and 10n. To communicate what I is, you write down I in binary. That takes you log of 10n bits. And she has to communicate I, and she has to communicate the ith symbol of her code word. The ith symbol of a code word also takes log of 10n bits to transmit, because whatever Reed-Solomon code you're using, this symbol, the alphabet size has to be larger than the length. So to transmit any symbol of the code word also takes log 10n bits. So the total communication looks like log 10n plus log 10n plus 1. You work out the parameters. I thought if n was 1,000,000, in the first scheme you were communicating 1,000,000 bits. In the second scheme, you were communicating only 47 bits, and you got it right with 90% probability. You can make it right with higher probability by spending a few more bits. So this error correcting codes we're not trying to get correct from errors or anything, but in a very different situation, you're just reducing communication significantly in order to carry out some task.
So there's a small question in the chat that we are assuming that Alice and Bob have already communicated the choice of alpha.
Very good question. So yes, I am assuming that Alice and Bob have, and this was important to do, that they had to agree on a code from before. So yes, so we are imagining a situation in which, maybe the whole world agrees on an encoding scheme for codes. And in cryptography, this assumption that everybody knows some encoding scheme in advance is often an assumption people make, and it's an assumption we can implement also in real world scenarios in various settings. So yes, what is the Reed-Solomon code you were using? What kind of code? So I talked about Reed-Solomon codes. You could use any error correcting code, right? There was nothing specific about Reed-Solomon we were using. And so which code are we going to use? That decision had to be made in advance. Absolutely. So how are we going to do this? What scheme are we going to use? Had to be pre-decided. Then Alice and Bob go to different parts of the world, and then Alice finds the string X and Bob finds the string Y, which they want to decide whether they're equal or not.
And there's a follow-up question, that is the amount of bit communicated independent of alphabet size?
It's not. It was 10 log n, right? So our alphabet size is going to end up being a function of the length of n. So if your message was length n, we will need the alphabet to be of size at least n or 10 times n. And so the number of bits got communicated ended up being log of that 10 times n. So it's not independent of n. But the dependence is only logarithmic in n as opposed to linear in n. So though there's dependence, and you must have dependence, you can't do it without that. That's known that this is basically tight. You can't get away with much better communication. But it's not independent of n. You do need it to depend on n. But the dependence is much milder than, instead of sending 1,000,000 bits, you just send 47. So it does depend on n, but very mildly. Okay, so there are questions to think about. How will you make the error probability small? How does it affect how much communication you do? Here I got error 10%. If I want to make the error 0.01%, how many more bits do you need to communicate? How would you modify my scheme to make it that that's a good question to think about. I know I'm mostly out of time, right? So let me wrap up. I thought I'd tell you about locally decodable codes, but let's not worry about it. So I can locally decodable codes are codes where you want the decoding algorithm to not even read the full code word, but just look at the code word in few locations. If I want to recover the true value at one location, I want to be able to do this by just looking at very few locations in the code and then being able to recover the true value at one location. Locally decodable codes again have, that's a very, in the last couple of decades they've received a lot of attention. You can use polynomials again to construct such codes. I talked about univariate polynomials for Reed-Solomon codes. You can use bivariate polynomials and trivariate polynomials and higher degree polynomials and do things with them and construct these things called locally decodable codes. Let me not. These codes also have good distance. And suppose I had a bivariate polynomial which you evaluated a bunch of points, and these bunch of points look like a grid. To recover the value at any line, you can pass a random line through it. The bivariate polynomials restricted to lines look like univariate polynomials. And then you can, hence by looking at much fewer locations, still recover the points at certain points. But let's, for those of you interested, Google for Reed-Muller codes and locally decodable codes, and you'll find lots of information of how you can use higher variate polynomials to do very nice things with codes. Okay, so you can do. And so there's talking in locally decodable codes, it's very interesting to ask not only what's the best rate and distance trade-off that you can achieve, but what's the best locality. So you want to get decoding algorithms without looking at the full code word, but just looking at maybe 10 locations of the code word or root 10 locations of the code word or whatever. Like what's the smallest number of queries you can make to your code word in order to decode it locally or decode the correct value in one location. But I'm out of time, so let me wrap up. And I'm happy to discuss, take questions and answer anything, other doubts that people have that I may not have answered. So I just want to say that there have been many nice, beautiful, fundamental questions about codes which are still open. And the most important one, I think, is what is the best rate distance trade-off you can achieve for general codes. So for binary codes over the 0-1 alphabet, we don't know that for any given rate, what's the largest distance you can achieve. We don't understand the answer to that very well. Many algorithmic questions, for each code that you design, ideally you want a code which is good but also has really efficient encoding decoding. So that's a very rich area of study. And then I didn't get time to talk about this question of sublinear algorithms, where you might have a huge amount of data that you encode, but then so for instance, you might want to encode, you have the English dictionary and you want to encode it or to store it on a DVD. Later on, you want to find the meaning of one word. To find the meaning of one word, maybe you don't want to decode the whole dictionary and pass it through an error correcting code. Like, that's really wasteful computation. So can you do something clever? Can you encode it in something called a locally decodable code, which will still, you want to be robust to many errors, but to recover a small piece of data, you want to be able to do it by looking at only a small piece of the code word. So that's, and then you can ask what's the best trade-offs you can have in rate, distance, and locality. Okay, so that was, I will end here. Thank you all very much. I'm happy to answer any questions which I might not have answered already.
So there's one comment on the chat about the Reed-Solomon code, that if we increase the distance, then the error would decrease, but it would also increase the amount of communication.
Yes. If we increase the
if we increase the distance, then the error would decrease, but it would also increase the amount of communication.
Yes, exactly. It would increase if we increase it. So absolutely. So it's a trade-off. If I want the error in that scheme, this communication complexity scheme, if I want the error to be not 10%, but I want the error to be 1%. Like, what's the error I'm willing to tolerate? Maybe I'm willing to tolerate 0.01%. Then I do need to so exactly what would you do? You would create a code of larger distance. To create a code of larger distance, the code word length would increase, and when the code word length increases, then the amount of communication increases, because instead of 10 log of 10n, maybe you're communicating log of 100n or a log of 1000n bits. But even a log of 1000n, think of error being 0.01%. A log of 1000n is much better than a million, even if n was large. So it is true, it increases the communication, and it's a good thing to calculate how much it increases the communication. But it turns out to be still the actual amount of it does increase it, but it doesn't increase it by much, and so it's a trade-off. And so I'm just saying it is still a much more, if you can, it's okay if you're okay with handling some error, 1% or 0.01%, it still gives you a vastly improved communication complexity as opposed to the original scheme, which was just gives all n bits over. So I'm just, but it is true, if you want to decrease the error, the communication will go up. That is true. So there is a trade-off between your error tolerance and your communication.
Good morning. I guess it's morning for you, Professor. Like, really enjoyed the talk. I have a question about, again, this communication complexity, like with the Reed-Solomon codes. So while the number of bits that you need to communicate is logarithmic in n, right? What about the time, the time required to actually compute the Reed-Solomon codes, right, on either end would be linear in n, right?
Yes.
So.
Yes.
Are there ways to actually reduce the amount of time you require to also compute? Are there any codes or any schemes where you minimize both the compute, like, or at least reduce the communicational complexity by like a really large margin, but also the computation of the code or the scheme by which you
It's a
transfer?
good question. So here we were assuming, yes, that the maybe linear in n time of computation is easy to do, but the communication was the expensive part, and so that was the part that we really needed to we were trying to optimize, and we managed to optimize the communication. Trying to get away with less than linear size in time spent, I have a feeling that one can prove that you cannot do it. One should be able to prove that if you want to indeed, like, if x and y differ in just one location, and you want to with 90% probability detect that they are different, even if they differ in one location, you need to at least look at all of x and all of y. Even looking at all of x, or reading through every bit of x. So even if Alice and Bob were in the same room, okay, there's no communication happening, they're both sitting in the same room, they both have x and y in front of them, and you want to decide is x the same as y or not, and you want to do this with very tiny error probability, you still need to spend linear time to even look to compare x and y with each other. You need that linear time. The encoding of Reed-Solomon codes is a little bit more than just linear, in that you have to consider the polynomial, and then you have to evaluate the polynomial. Maybe it's n log n or something because you can not only look at x, you have to from it construct a polynomial and from it evaluate. And so can you do faster there? I don't know the answer. But linear, I think you have to spend. You're not getting away without spending linear. But doing better but just getting just linear, like time 2n of in time 5n, what's the best you can do? I think that's a good question. I don't know the answer to that.
Okay, thank you for answering.
Thanks for asking. Yeah.
So there's also a question in the chat. In real life applications, is there an actual guarantee or condition that there can be a maximum error of n bits? Or is there some tiny probability that the number of errors can exceed n bits?
So n bits was I'm guessing n is the length of the code word. So if n is the length of the code word, and the number of errors is more than n bits, which means the whole code word can be destroyed. I mean, that could happen in real life. Like you store your data in some data center and the building catches fire, right? And then your data is gone. So the error is more than n bits. So absolutely, in real life applications, there are situations when that can happen, and then you need to be robust to even that. I mean, there may be situations where the error is really large, and there's really nothing you can do. N errors for a string of length 2n plus 1. Okay. Can errors exceed? So you're saying, okay, maybe you don't lose all the data, but you lose half the data. And the question is, can you do something? So, okay, good. So I don't know if I fully understand your question, but basically, in real life situations, you can have lots of errors, and you have to, when you design an error correcting code scheme, you design it to be robust to some number of errors. If you messed up in your assumption that the number of errors would be small, and actually the number of errors was more than you expected, then you're going to pay for it. You will not be able to decode your data. And indeed, it happens in real life situations. That happens, that people design error correcting codes to protect from some number of errors, and then the number of errors, and your assumption is wrong, the number of errors is too much, and in that tiny probability, hopefully it's a really tiny probability event, you lost all your data. So there is no actual guarantee. You can only monitor the conditions or probability of a I don't know, fire or erasure. Yes.
So I was thinking, like, what happens when you compare the Reed-Solomon code with that tiny probability? Like, if you reduce the or like you increase the efficiency so that it accounts for that tiny probability, then what's more efficient, like a regular Hamming code or that?
Good. So, okay, saying that the probability, you're saying, maybe in most situations, that there's one error, but with some probability, there'll be a lot of errors. So then should you use the Hamming code, or should you use Reed-Solomon if you know that the probability for many errors is small? Right. It also depends on it's the probability of errors and how much risk you're willing to tolerate. If when Google is storing all our emails and they use error correcting codes to store all this data, maybe Google cannot afford for the tiny probability that everybody's email and data is lost, right? So then they would have ways to make it really robust. You cannot afford even the 1% probability of losing data is too much. And so it depends on the cost. If you're okay with the 1% probability of losing the data, then you can model that and you can say, okay, fine, I don't need to use the most amazing error correcting code. I can, with high probability, if I use, I'll only have 5 corruptions, so I can use this other code, because the loss to me of of losing all the data I can handle. So it really also depends on your risk or your tolerance for losing the data. Even if there's a tiny probability of losing the data, in some situations you absolutely cannot, and then you need to have an error correcting code which has enough redundancy, like the Reed-Solomon code. Or it's okay with you with 1% probability to lose the data, and then yes, maybe you can not use Reed-Solomon and you can do better.
Thank you.
There's another question in the chat. So what are the broad ideas that people have used to design codes? So for example, we have seen geometry or algebra. So what can be some different approaches?
People use something called expander graphs. That's a very common. I don't know if you've seen these graphs, expander graphs, but using combinatorial ideas and graph theory, that's been there have been lots of studies of codes using that. So people use all kinds. I mean, codes come from all kinds of areas of math, and graph theory and expander graphs is one well studied and a rich area for designing codes which are good. Like, they have distance, and you can use properties of these graphs to do efficient encoding and decoding and things like that as well. So algebraic methods are very popular just because they're neat, clean, we understand them well, and the algorithms are good, but there are lots of combinatorial approaches for constructing codes. And randomness and random walks and things like that show up a lot.
And there's also maybe side question, but it is like sometimes it is really difficult to come up with lower bounds. So how do people approach such problems?
This is nothing to do with codes, you mean? Just complexity theory, or with?
I think it is just complexity theory in general.
No, I mean, even in like coding theory, when we communicate, we have some space bound and time bound, right? So what is the minimum space that we need to communicate, or like what is the like minimum amount of queries that we need to make to know that like
Right. Lower bounds are really hard. Yeah. How do you approach such problems? I mean, you'd have a. I don't know. So even in codes, I mean, some lower bounds are known, but in general, I mean, there's some basic bounds we know. But you talked about number of queries. So for locally decodable codes, how many queries do you need? And it's lower bounds in general. They're hard, which is why we know very very few. Like in the lower bound space, we just. We believe much stronger lower bounds to be true in various settings, and we are able to prove much less than what we believe to be true. So I don't know. I don't have a good answer. If I had a good answer how to approach these low bounds and prove them, I mean, people would be trying to do them, and I would be trying to do them. And in general, they're hard. You just have to, I mean, have faith and at least try, and a lot of nice math comes out of it. I mean, ultimately proving a lower bound, showing that some object exists, means some nice mathematical structure must exist, and you need to show that that nice mathematical structure does not exist. Often it really is depending on each situation. You have to understand enough, have enough faith. And it is really hard. I mean, I wish I had a good answer. Prove lower bounds for the length of 3 query locally decodable codes. I mean, this has been a question which has been open so long. The best codes you have n being something like, I don't know, 2 to the, I mean, something exponentially large. The best lower bounds are n square. I mean, we believe much better lower bounds to be true. We just don't have the techniques to do it. Lower bounds are hard. I don't know. I don't have a good answer.
There's another question. So can we reduce this problem of error correction and communication to some other well-known problem? Are there other problems which can be reduced to error correction?
So error correction. So error correction itself was, I mean, just as the way I describe it was as cleanly defined as, I mean, you want to find points spaced apart inside you in this space sigma to the n. Find a way of getting a whole bunch of points which are far apart from each other in sigma to the n. Pack as many points as you can in sigma to the n, any two being far apart. And that was the combinatorial question. Can you reduce any other problem to it? I don't know. But there are techniques in studying error correcting codes which are very, the same kinds of techniques give you other objects. So maybe in some sense, they're very similar techniques which in the study of error correcting codes, which might be used in the study of other objects. And one such technique is so there's a whole theory of pseudo randomness. So often you can construct good error correcting codes using randomness as a technique. Like one good way of constructing a code is just to randomly choose a whole bunch of points inside sigma to the n, and then hope that any two will be far apart. So you randomly select points. You can randomly select. Oftentimes, this random selection process, we know how to prove better guarantees that with high probability the distance will be better than what we know how to construct deterministically. Like we don't know how to find a good code by using algebraic methods or any other methods, but just pick a random code. Often that act is, we know how to show that with like very high probability that object is going to be a good code. So, but what do you mean by pick a random code, right? I mean, a random code will only be good with high probability. Maybe I want a code which is always has good distance. So you want to de-randomize the process. I know that a random code will be good. I want to get a fixed code which is good. So I want to somehow you deterministically de-randomize whatever this randomized process was. And this is like there's a study of something called pseudo-randomness, which is trying to design an object deterministically, but has the properties that random objects do. And so often the design of error correcting codes or good error correcting codes is quite tied to other questions in pseudo-randomness, or in trying to deterministically create objects which have random-like properties. And then in theoretical computer science, you use pseudo-randomness comes up in different settings, and often, I mean, error correcting codes are quite closely tied up or linked with these objects.
And maybe I have like one question all related to this. So like what I guess is like all these lower bounds or whatever we have, like these are unconditional, like they don't depend on any assumptions.
Okay.
Yeah. So like does it help to assume some, like maybe assume that P is not equal to NP or something, like complexity theoretic assumptions? Does it help, or that is
Yeah,
not?
that's a good question. We don't know how to, for the error correcting codes, at least, since this is not the design of error correcting codes is not a computational, it's computational.
Right.
I'm okay to spend exponential amount of time to design my codes. I'm okay with spending, so it's not a computational question at all. I mean, for algorithms, for decoding and encoding, then you can talk about the computation. But the more fundamental question which is the combinatorial question, which is just design a code, show that there doesn't exist a collection of points of so many points with so much distance. It's become very combinatorial, that question. There is no time complexity. So whether P equals NP or P not equal to NP doesn't affect the answer here at all, because do they exist, these good codes? I mean, I'm okay with spending exponential or double exponential or triple any time complexity to be able to answer the question. So at least for the existence of good codes of good rate and good distance, I don't know how to do it using time complexity assumptions. One could possibly have, I mean, there may be algorithms. We might be able to design a particular kind of code and say, look, this algorithm is going to be good or bad. I mean, the running time of encoding and decoding, perhaps one can talk about with assumptions. Or, yeah, and there's, right. But in the coding theory context, again, I don't know of any such interesting ones. But the basic question, yeah, we don't know how to do it with assumptions. I don't know how to, yeah.
So I think we can conclude this session. Yeah. So thank you once again, Professor Sharaf, for this beautiful and amazing talk. It was really simple to follow through all the slides, and it was also amazing to see how simple to describe the Reed-Solomon code was, and it turns out to be the best possible code. And thank you for all the questions. Like I think now people will go and Google all these codes and read about more of them. So it was amazing, and thank you once again for accepting our invitation and taking your time in your busy schedule to talk to these people on a Saturday morning for you. So thank you once again.
Well,
And
thank you. Go ahead.
And yeah, and just the final thing, the final lecture of our lecture series will be on 4th December at 4 p.m. by Professor Kavita Telikapalli on fair division, and hope to see you all there. Thank you, Professor Shubhangi, once again.
Thank you, Amik. Thank you all. It was a pleasure. Thanks all for the questions and making it interactive. It was really fun giving the talk. So thank you for inviting me, and yeah, thank you.
Thanks a lot, Shubhangi.
Thanks, Aniruddha.
Thank you.
Thank you.